Hi, it's Matt, and I want to introduce Mangle to you quickly. Mangle is a virtual machine for transforming and generating strings of characters. You might find use of this if you've ever wanted to create fantasy worlds or sci-fi worlds and wanted words that didn't sound like ordinary English words but sounded like they could have been English words or some other language. And unless you are the kind of person where these words pop into your head unbidden, a tool like this for creating words might seem interesting. So it's a virtual machine. What does that mean? It's a machine that runs an instruction set, and here you can see the simplest example of a Mangle program. And if I was to run this program and I give it a word, I give it the word hello, you'll see what it does is it gives me the word hello back. So let's just take a quick look. So every Mangle program starts with a label start, so that's start colon. Comments run from a hash to the end of the line, and this is the program that returns the input word unmodified. So it has one effective instruction, which is load W in, and then it runs halt. So what this does is this loads the word register W with the value of the input register. The input register is whatever is given here. So if I change this, you'll see it gives us world. And we could see that by putting in log in here into this, and that will show you that the in register contains the word that we give it. And the way Mangle works is when the program halts, whatever is in W is what gets returned. So what we could do here is we could say world here, and now when we run the program, even though we give it hello, we get world back because whatever's in W is what we get. Okay, so far so good. Let's look at a slightly more complicated example. So this one, based on the value of the I1 register, so I stands for index, and you have a set of index registers which can hold numbers, which could be characters or indices into word registers. So in this case, we're using I1 to say, should we shuffle or reverse the back half of the input word? So we do the same thing again, we load in into W, and then we load I0 with the value of W.len. So string register properties like in and W have a length property. So in the case of this, if we load this one, and we now pass it here, and let's log this, log I0 will halt just to stop at that point, what you will see is I0 is 2. We take the length of the word is 5, we divide it by 2, we're doing integer division here, so we get a result of 2. If we gave it the word fish tank, we would get 4. So that's doing a little calculation, and then it's doing a comparison. So it's saying, what is the value of the I1 register? Now, by default, index registers are initialized to 0. So effectively, we've run this instruction. So in this case, this will always fail because I1 is 0. And if it fails, that means it will fall through to the next. This jump OK will jump if the previous instruction was a success, if it's set what's called the condition flag to true. This will fail, and therefore the condition flag is not set to true. This jump doesn't happen, and we end up in this reverse. So if I1 is 0, we're going to be reversing this. We're going to use this reverse instruction. If I1 was 1, and we'll work out how that could happen in a second, we would take this jump to shuffle, and we would shuffle, and then we're done. So what does this do? It's reversing the back half of the word. That's because the reverse instruction takes an index, which in the case of fish tank is going to be 4, half of the length, and a number of characters, which is the same in this case. What we could do is we could set this to 2, and if we did this, it would reverse only 2 of the back half characters. Now there's a number of ways that I1 could be 1. One way is we can actually pass the initial value of registers via the command line, and what you'll see now is every time we run the program we get a different shuffling of the last 4 characters of the word. So let's jump to the next example. So this is a bit more complicated again. It's making use of what are called table registers. So we're loading a table register V with the English language vowels with a relative frequency that is the same. So this is not English letter frequencies, although it is English letters. And we're loading table C with consonants. Now what we're going to do is, and this is quite a common pattern for transforming words, is we're now going to scan through the input word. So we've loaded the input word into W. We load the cursor register C. C is used for indexing into W. And what we're saying here is C past the end of the word? If it isn't, carry on. If it is, we're done. Obviously at this point C is 0, so it's not past the end of the word. The last index, which is what this li property does for the word fish tank, would be 7. 0 points to the F, 7 points to the K. So C being 0 is not greater than 7. The condition flag is false. This jump doesn't happen. And so it does a little bit of work. So now it uses another new instruction called match. And match says, is the character in string register W at index C matching this table of vowels? And what that means is this character any of these characters? Again, that will set the condition flag to true if it is one of these characters, or false otherwise. So if it's set to true, this jump OK will happen. We know that character is a vowel, and we can jump over to here to replace vowel, which is going to use the replace instruction that says replace the character in W at C, again with TV. When you are loading from a table register rather than matching a table register, it will give you a random character based on the relative frequency of the characters in that table. So in this case, we'll get an equal frequency of all of these letters. Similarly, if this doesn't match, this will not jump, and we will then match a constant. Now, if it does, we go to replace consonant, which does the same thing, only with the consonant table, and then jumps to the next character. And inc C means we now look at the next character and we jump back to here and we say, is it? So it'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, and at the point where it's 8, it will halt because it's done. So what does this program do? Let's have a look. So we give it a word, fish tank. We don't need to initialize that register anymore. Now, what you'll see now is we're getting completely randomized words, but following the pattern. So fish tank is consonant, vowel, consonant, 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 vowel, consonant, consonant, and you'll see Vaxvaft is also consonant, vowel, consonant, 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 vowel, consonant, consonant. So we're actually going through and replacing every consonant with a random consonant, every vowel with a random vowel, but because we're using equal frequencies, these do not look like English words. So let's look at our last example. This is a little bit more complex again, and what this is doing is it's now using the frequency map version of loading tables with English letter frequencies. Fundamentally it's doing a similar kind of thing, only now what it's doing is matching clusters of consonant, vowel, consonant and so forth, and then replacing them with an equivalent cluster. So in this case we can replace CVC, we can replace CV, VCV or VC. So in this case, if we run this program, we will get a slightly different result, which looks more like an English word. Not much more in this case, but you can see Rish talk, while it's not actually an English word, could be an English word. Nefosk. Now, there's more complex rules about how English words are constructed that are not part of this program, but you can see how this program is scanning, looking for things, generating things. Included in the Mangle release are things like a Fremen generator. So this uses my friend Chris Bateman's Fremen language schema from his Outlands RPG. Generators work slightly differently. Here, instead of passing a word, because of the way this works, we give it a number of words we want, and it will give us back words. And some of these sound like they could come out of Dune, Dur, Gaze, Jawa, Gale. These potentially sound like Fremen words, and Shivan, which was an original creation of his, which has a completely different feel to it. And making your own generators like this is relatively easy. This program looks complicated, but actually isn't particularly complicated. So that's Mangle. It can transform words using rules, it can generate words using rules. It's kind of fun to play with. The last thing is it does have a debugger, so if you're wondering how any program works, you can run it with debug. You can drop into a debugger which allows you to list the program, single step. You can set breakpoints, and basically basically allows you to debug and understand. So what is in TB now? We can see it's a table with these different character sets, and you can see tables have trigraphs and digraphs, in this case just digraphs. So you can actually run this in a debugger and understand exactly how it works. So that's Mangle. If you find it interesting, that's great. If you generate some words with it, even better. Thanks for watching.